Hello and thank you for tuning in. To kick off 2019, we'll be starting with a webinar focusing on flood model calibration. This is a rehash of a workshop that we hosted at the 2017 FMA conference in Long Beach, California. We've broken the presentation up into three separate segments. We'll start with why calibration is necessary, follow it up with some common data preparation steps before we look at a real-world case study. Why is calibration necessary? Calibration is really the only true way to verify that the models we create are representing the real-world conditions, or representative of real-world conditions, and producing a flood behaviour which mimics reality. I'd like to use this dam break flume test as an example to demonstrate why verification against recorded data is important. What we have here is a reservoir on the left, a gate in the middle which opens up, representing a dam break, and then a bleak building midway down the flume on the right-hand side. Surrounding that building, there are some recorded data recording locations for measuring water level and velocity. We've translated that flume into two models. The model on the top is one which uses TUFLOW's default parameters, and then the one on the bottom is the exact same model, though with eddy viscosity terms switched off. The question I'd like to ask you is, which of these two is right? When I've asked this at previous presentations, I've presented this data a number of times now, the majority of people typically guess that the answer on the bottom, which shows the chaotic flow behavior, is most likely the correct answer. And the reason for that being it's a dam break, they'd expect some chaotic hydraulics downstream of that dam break. It's not until we actually look at the recorded data that we can really tell which one is right or wrong. If we look at those graphs, I'm just focusing on two locations here. The graphs along the top are presenting water level result. Those on the two on the bottom presenting velocity results. The target that we're hoping to match in all cases here is the black line. That's the flume, or the recorded data from the flume test. The blue line on these graphs reports the result for what was the top animation. That was the one that used TUFLOW's default settings. And then the red line, which in all cases here shows quite a poor result, comes from the model that didn't use the eddy viscosity, or had the eddy viscosity terms switched off. So this is actually a great example showing where a model result which looks quite convincing is actually extremely wrong. The one without viscosity turned on doesn't approximate the real conditions at all, whereas the one using TUFLOW's default parameters does. And the same goes for real-world situations. We really need to calibrate our models against historic events to make sure that the features we include in those models are producing the correct flood behavior. I've derived a really quick calibration workflow here, and this is what I'd normally apply during a flood study. To start with, I confirm the accuracy of all my inputs before use. That relates to inputs to models as well as the verification datasets I'm comparing against. When I go about creating my model, the first thing I do is work out what cell size I should be using so that I can achieve cell size convergence. If you're not familiar with what that term is or what it means, I recommend tuning into looking back through our YouTube channel and watching the webinar that we posted last year on the topic. Having done that, I'll then set my Manning's N definition for the entire study area. So I'll categorize that and set values that represent industry standard values. And having done that, the first thing I'll do is I'll usually calibrate to a small event. Now, the reason I focus on a small event to begin with is that way I can really test or tune in the definition of the conveyance zones within my model before stepping up to a larger calibration, or a larger event to calibrate to, which would then be impacted by both flow within the conveyance zones as well as in the storage areas of the floodplain. This is a 5-step process. It's actually not a linear workflow. The last 3 bullet points here do require iterative refinement to create a model which works for all situations. Let's start with looking at some input data preparation. With all hydraulic modelling, the quality of your input data has a direct impact on the quality of your results. There's the old saying of rubbish in equals rubbish out. So it is very important that all of your inputs to a flood model are of high quality. I would start with collecting LiDAR data of my study area and then also survey of key hydraulic features. And those are typically levees, raised road or rail embankments, bathymetry data sets, and then also any necessary structures that could influence the hydraulics, that being bridges or major culverts. In all cases, I'd be checking the elevation data associated with these data sets to make sure that the datum is consistent with what I'll be modelling in, with my hydraulic model, and also check that the projections match. Further to that, wherever possible, I also compare against secondary data sets to verify the accuracy. And the histogram on the right demonstrates this. This is an example of where I've compared LiDAR data that became the base topography for my model against 429 surveyed benchmark points in a catchment. Those sort of cross-checks are very important to make sure the data you're putting into a model is correct or is accurate. Having prepared all of my topographic data, the next thing I'd look at is my land use data sets. And I'd typically start this by doing a site visit just to familiarise myself with what's on the ground and the location where I'll be modelling. After doing that, I'd classify the land use categories across my whole model domain and then apply industry standard manning end values to those different delineated areas. Now, I often receive questions from new users relating to Manning's End, in particular asking what value I should be applied for what type of vegetation. And I typically point those users to 2 documents. The first is on the left here. This is the Australian Rainfall Runoff 2D Modelling in Urban and Rural Floodplain Guideline document. In this document you'll find section 10, table 10.1, provides an overview of what is considered industry standard. Further to that, I also like to point people at the Brisbane City Council Natural Channel Design Guideline document. Similar to the AR&R document, it has a table of values, but further to that, it also includes specific pictures of different scenarios and the Manning's End that should be applied relating to that picture. And this is really useful for new users who are trying to just get an understanding of what value relates to what sort of roughness. The next thing I typically look at are my boundary condition data sets. We'll start with tidal data here. In the vast majority of cases, you'll find that the elevation datum associated with tidal data doesn't match the elevation datum of your flood model. The simple reason for that is the primary purpose of collecting tide data is to ensure that the draft of boats isn't too deep to operate in navigation channels in ports and rivers, so they relate their levels to lowest astronomical tide. So this typically needs correcting to be applied into a flood model. Similarly, we need to check our historic rainfall data sets to make sure that all of the gauges that we're using as inputs to our model were operational for the entire duration of the flood event we're hoping to model. Now, I check this in a variety of ways. The first thing I typically do is translate my time-varying rainfall data into daily totals, and I would compare that against neighbouring pluviographs, neighbouring daily pluviographs to see if there's a correlation or large variance. If there is large variance, then that could be indicative of a gauge that's gone offline during an event. I do some comparisons against radar data sets, compare it against anecdotal evidence from local residents. I also typically do an analysis where I translate time series data, such as you're looking at here, into a cumulative format. And by doing this, if I can identify gauges that exhibit horizontal cumulative rainfall totals, this is typically an indication that that gauge may have stopped operating during the event, as was the case in this situation here. These two gauges are actually in the location of the catchment that received the most rainfall, but the gauges didn't pick up the information because they stopped working in the first quarter of the event. So obviously, if we were to apply this data without checking it carefully and filtering it, then the flood model results wouldn't calibrate well to the historic event because the inflows we put into the model are wrong. So far we've been focusing on model input data sets. Now we'll look at the calibration data for which we're comparing our model results against. And we'll start with gauge water level recordings. The first thing I usually check here is the metadata set associated with the gauge. Gauges that have been around for a very long time may well have changed their location during their life at some point. In addition to changing their location, they may well have changed the datum for which they reference against as well. I also check for consistency in surrounding gauges by plotting them up against each other. Here I'm looking for just logical trends in arrival time and levels. If I don't see those, often I'll go back to the data provider and just make sure there's no error in their data processing routines. Gauged water level recordings are often translated to flow estimates using rating curves such as this. Whenever you compare flow estimates at gauges against model results, it's important to look at the metadata for that gauge, and there's a couple of reasons for this. What you're trying to do here is work out how the gauge rating has been derived. Here's an example where lots of gaugings have been undertaken for low flow events, but none for high flow events. An extrapolation of the recorded data has been used for the upper end of the graph. Now the issue with this is that where the real flow water level relationship sits could be drastically different from what's shown in the rating curve, and therefore if you're comparing your modelled flow against this rated flow, you could get a drastically different result, and it wouldn't be the fault of the model, it would actually be a fault of this rating curve. So in some cases you'll find that the upper end of these graphs have been extrapolated. In other cases you might find the agency has used an approach to try and estimate what the flow water level relationship should be. In a couple of cases there I have found that the agencies have used the river cross-section for that estimate without accounting for the fact that when a flood occurs, a lot of the flow breaks out of bank and goes into the floodplain. So they've actually underestimated the flow because they haven't captured the cross-sectional characteristics of the out-of-bank flow in their rating. So just something to be aware of there. Surveyed peak flood debris marks also need verification prior to trusting them as for model calibration. There's a couple of things I typically do here. Normally I'll just take a broad brush approach just to check consistency across all of the debris marks to make sure that the trend in water levels seems logical. Also, when I'm looking at quite old data sets, or when we're trying to calibrate to really old events, I do a bit more further investigation just to make sure the values seem logical. There was one situation where I was working on one study where we were trying to model, it was an event that occurred in 1989. One of the local residents had marked the flood level on their house for that event, which we were trying to calibrate to, and unfortunately there wasn't many other flood marks for that event, so we were really just tying to a handful of marks. Unfortunately, the flood model seemed to underpredict the flood by around about 1.5 meters, no matter what we did. And through subsequent investigation, it turned out that between the late 80s and the date that we were working at, which was in the mid-2000s, that house had been raised. It had been placed on stilts. So once we account for the fact that the house had been raised, the flood mark tied in quite nicely with the flood model result. Finally, the thing that is often overlooked is anecdotal evidence. There's a lot of value in collecting observations from local residents and taking out anecdotal evidence from things such as newspapers from the past. That way you can just make sure the flood behaviour that's being observed in your model translates and relates well to what happened on the ground during an event. Having gone through and checked all of our data inputs, it would now be the time to actually start building our model and calibrating it. And here I'll provide a real-world example. This is a data set that's been provided by Clarence Valley Council. It's the Lower Clarence Flood Study model. It was recalibrated in 2013. I'll go through a quick overview as to why it's such a good model for this purpose, for this demonstration. A full report of the calibration is available on the web if you just search for the title that was on the previous slide. In this presentation, we'll just focus on some key data sets. But to give an overview of the catchment, we have 25 gauge locations in the lower catchment. So it's an extensive network, both along the main channel as well as its tributaries. It has a long flood history. It goes back over 100 years, but more recently, since the major levee developments in the catchment, there have been 8 significant floods, of which we've calibrated the flood model to. The benefit of calibrating multiple events is that you can create a flood model which works for the full spectrum of floods, from minor flood events through to major flood events. In addition to the gaugings, there's also been detailed velocity surveys done during about a dozen floods in the catchment, and this has been used to derive a rating in the main Clarence River, which has been subsequently compared against our flood model just to make sure there's a correlation between the two, which there is. Finally, Council has been very proactive in their data collection following flood events. There's over 600 surveyed peak flood levels covering 3 events, so 2001, 2009 and 2013. And these are excellent for providing a really detailed image of what's happening in the floodplain during these events. Now, in terms of what we'll present today, there's obviously too much data to cover in the 10 to 15 minutes that I'd like to spend on this calibration demonstration. So instead of focusing on all 25 of those gauges, I've chosen 3 select locations: Grafton in the upper part of the model, Brush Grove in the central region, and then McLean in the lower part of the model. And I'll also give an overview of the surveyed debris marks in that upper half of the model. Obviously, looking at the whole catchment would just be too large, and there'd be too much detail to try and capture in such a short amount of time. Let's have a quick look at the model itself. We have the Clarence River inflow, which is shown by the blue arrow here. It accounts for approximately around about 80% of the inflow to this entire model. We have numerous external tributaries shown in pink. We have the river entrance, where we have the tide coming in and out, and then internal within the model, the hydraulic model domain, we have internal catchment rainfall. When we updated the model with the most recent LiDAR and reran our calibration events, this is the type of result that we got. I'll be showing 2 events of the 8. That's just the 2001 event and the 2013. These here are the 2001 results, and you can see that it's pretty poor. 2013 shows a similar trend, quite a poor calibration. We're really over predicting the flood. If we look at the recorded, the surveyed debris marks, you can also see that we're over predicting flood levels in the floodplain. The numbers here on the right are listing the flood level difference this is in feet, not in meters. It's the model result minus the recorded value. And the histogram on the bottom left is showing a summary of that complete data set. Ideally, I'd be hoping to get the recorded level within, and the model result within what plus or minus 1 foot of each other. That's typically considered a good fit. So this is now the 2013 event result, and it's also quite a horrible calibration. What could be the cause of the poor fit? It turns out the LiDAR data didn't include any bathymetry information. So we weren't representing the conveyance zone of this catchment well at all. And it was meaning that water levels in the river were too high, and then it was also pushing too much water out into the floodplain. So the first step in the calibration was to fix that and to add bathymetry to the model. And all of a sudden you can see that the results improve dramatically. I mean, this looks like quite a good calibration now. That's 2001. This is 2013. Here we're looking at our surveyed peak flood marks in the floodplain. They actually look a little bit too high in a lot of locations, so up around probably 1.5 feet too high, or maybe even 2 feet too high for 2001. And we're seeing a similar trend for 2013. Levels in the floodplain are a bit too high. The histogram style of reporting is actually a good way to identify general trends such as this. And then once you know there's a general issue with your model, you can zoom in and isolate the particular location where it's occurring. Now it turns out, in its previous form, the model didn't include any breakline data sets for the key hydraulic controls. So that includes raised road and rail embankments, perched riverbanks, levees, and also minor drainage channels. So we'll add those features to the model, and we'll see how it changes the results further. In this image here, the pink lines are areas where break lines have been used to raise elevations, and the blue lines are where they've been used to cut in lower elevations for drainage channels. Okay, so for 2001, the calibration looks quite good. Similarly for 2013. If we look at our recorded peak water level marks, now we're seeing a much better fit in the floodplain, whereas previously we were struggling to get within the tolerance that we were hoping to achieve. That's 2001. In 2013 we've also improved the calibration, now mostly sitting within that 1 plus or minus 1 foot tolerance. You'll notice I haven't spoken about Manning's N up until now. Typically I would try and lock in all of my topographic improvements, so elevation improvements, prior to even considering any changes or refinements to Manning's N. This way it ensures that any Manning's N updates I do make aren't compensating for other errors in the model. Young engineers who don't have experience in calibrating sometimes go straight to modifying Manning's N values, and as such end up using values that are outside industry standard just to compensate for things like missing the bathymetry in a river or not including break lines where they should. And obviously what Manning's N you select does impact the results. If you use figures and numbers that are within industry value and all the other topography is correct, then you should get a model that calibrates well, as long as your hydrology inputs are correct as well. Now the question is, does a calibrated model guarantee accurate design flood estimates? The answer to that is no, it doesn't, unfortunately. And the reason is that in some cases, with poor hydrologic parameterization, you don't see hydraulic transformation probability neutrality. What that means is you may have an accurate hydraulic model, and then when you apply your design rainfall of a certain recurrence interval, say a 100-year event, that model may not produce a 100-year flood. due to hydrologic assumptions that are associated with your inflows. So if you have your intensity wrong, or the duration or the temporal pattern or error reduction factor incorrect, you may find that the peak flows that your model produces don't translate well to what should be occurring on the ground or what does occur in the ground reality. Because of this, it's good practice to compare hydraulic design event hydraulic model results against flood frequency analysis data sets, just to ensure that the magnitude of flood event you're hoping to represent in your model does translate through to what is happening in reality. That concludes today's presentation. Thank you for tuning in. If you have any questions or any requests in terms of future webinars and presentations, please send me an email either at chrishuxley@tuflow.com or info@tuflow.com. See you next time.